The next thing I want to talk about is a linear combination. And before I do that, I'm actually going to give a graphical description of vectors. So let's consider the vector given by 8, -1. Well, there are other ways to represent this vector. Instead of a column, we could write it as a row, 8, -1. And in this form, we can start to see the resemblance between a vector and an ordered pair. And in fact, a vector can be represented graphically by an arrow that starts at the origin and ends at the point. So I need to go over 8 and down 1, and then I just draw this vector. So this means that our two-dimensional coordinate plane can correspond to vectors. Every single point in the plane will correspond to a vector, and every single vector will correspond to a point in the plane. And we denote this by this R2 in this special font called Blackboard Bold. Essentially, R2 means all the vectors with 2 entries. And we can extend this idea too. 3 entries would be R3. In the general case, Rn means that it's a vector with n entries. The R just means that the entries in the vector are the real numbers, and then the exponent tells you how many there are. Now let's talk about actually doing our operations on vectors. So we'll start with scalar multiplication, multiplying a vector by a number. The idea is that you're scaling the vector by a certain amount, and this is where this word scalar comes from. So if I have a vector and I want to multiply that vector by 2, I would just double the length. If I wanted to multiply by 1/2, I would half the length. And multiplying by a negative scalar essentially would just reverse the direction of the vector. So if I had a different vector here, multiplying by -1/2 would switch the direction and make it half the length. Let's consider vector addition. For this, we need to use what's called the parallelogram rule. The idea is that we have 2 vectors. We'll call this one y and this one x, so they both start at the origin. We're essentially going to draw the parallelogram that these correspond to. These are 2 sides of a parallelogram. And then we draw the diagonal of that parallelogram. And that gives me x plus y. If we draw the opposite diagonal down, this one is x minus y. So now what if we want to combine these? We want to use scalar multiplication and addition. We have some vectors, we scale them, and then we add them. Well, this is the idea of a linear combination. So we say z is a linear combination of vectors x1, x2, all the way up to xm, which are all in Rn. If z can be written as c1, x1 plus c2, x2 plus cm, xm. The idea being we're going to have a set of vectors, we scale them, and then we add them together. This would be a linear combination. Examples, 7x1 minus 4x2, where x1 and x2 are known. We could have x1 plus the square root of 5 times x2. We could have 3x2, which is equal to 0x1 plus 3x2, so we can write it as a scalar times these vectors. And we can also write the 0 vector as a linear combination, because this would be 0x1 plus 0x2.